Hi, welcome back. This is a video in graphing polar equations now. So we talked about plotting um, in the last section, and now we want to graph the equations. Okay, so the first method I just call basically the brute force method. And what you're going to do is make a big table and plot every point. Okay, so this is actually checkpoint 1 in the book. And they want you to plot the graph of r equals 4 sine theta. Okay, so you're going to make, instead of x and y, you'll have theta and r, okay, where r is a function of theta. Okay, and then I'm just going to graph a whole bunch of values starting at 0 and going by increments of pi over 6. Okay. You can pick smaller increments, but you have to worry about, can I evaluate those without a calculator? Usually you want to pick something you can evaluate. Okay. So 2 pi over 6, 3 pi over 6, we'll go all the way up to pi. 3 pi over 6, 4 pi over 6, 5 pi over 6, and then 6 pi over 6. Okay, and we're just plugging these values into the function r equals 4 sine theta. In particular here, we'll put 0 in for theta, so r equals 4 times sine of 0, which of course is 0, so that'll be 0. Pi over 6, so we get 4 times sine of pi over 6, which is 1/2, so 2. 4 times sine of, this will be pi over 3, so that'll be root 3 over 2. So that'll be 2 root 3. And let's get an approximation so we can graph the thing. It's about 3.46. Then 3 pi over 6 is pi over 2, so this will be just 4 times 1, which of course is 4. And then 2 pi over 3, sine is still positive there, so that'll be 4 times root 3 over 2. Again, 2 root 3, which is approximately 3.46. 5 pi over 6, sine is still positive, so it'll be 4 times 1/2, which is 2. 6 pi over 6, sine will go back to 0, right there, 0. Okay, then we just go to the polar coordinate system superimposed on the rectangular coordinate system and graph that thing. Okay, so it looks like we're going to need to go to 4 with the concentric circles here. 1, 2, 3, and then 4. And we need some kind of angle lines going by pi over 6's. So let's put those in a different color. Put those in blue. Pi over 6, 2 pi over 6, which is basically pi over 3, 3 pi over 6, 4 pi over 6, 5 pi over 6. Okay, and that should carry us through. Then I'm going to plot these points, right? So 0, 0 is just the pole. And then we have pi over 6, comma 2, which would be right here. And then we have 2 pi over 6, comma 3.46, 1, 2, 3.46, about right here. And then we have pi over 2, comma 4, and then it sort of just goes in reverse, right? So, 4 pi over 6, 3.46, and then 5 pi over 6, it goes back to 2. And then it goes in. Okay, so the way these curves are generated, it always kind of have a curvy flavor to it. So as you go through the points, you're connecting like this. My cat's having a bad day. And that's, it should be a circle, okay, is the end result of this graph. And one thing that's important is always to note where you've traced it. So we have 7 pi over 6 here. If you go the 7 pi over 6, you'll just repeat. 7 pi over 6 sine will become negative, and so you'll be forced onto the other side of the angle arm. So that's big. So 7 pi over 6, you would get 4 times negative 1/2, which would give you negative 2. So that would be back to this point here. Okay. It would actually be on this arm, but then you go negative 1. Oops. So that should be at 2. So I screwed up that first point. It should be actually right here, not out there. Okay. Okay. So that's kind of what these things will look like. In general, you want to think of these blue lines here, that of these radial or angular lines that I've drawn, as kind of rotating in the plane. And as they rotate, the R value is on that arm, and it'll kind of move around up and down on that arm. And as it does, it causes kind of a curve to come out. So you have this sort of radial arm moving in a circular motion around the pole, and then on the arm you have basically this dot, which is kind of going in and out according to wherever the heck it is. The curve that results will always be this kind of curve, a sort of a circular type motion resulting. Okay. I look for some animations online, and usually I have Wolfram, but Wolfram's license, believe it or not, only applies to me while I'm at work, so I can't use it on my home computer. In other words, I'm not able to access that. But if you go online in YouTube, I was just looking around, they have some okay visualizations, but they're not, I don't want to use somebody else's content, but they kind of go through and show you how the graphs are being traced out. I don't know. So you can kind of see how the arm is moving, and then on it, there's the graph is being traced out. So there's this moving R value on the arm, and it's tracing out the graph. And of course, this guy has a lot to say, so he's not going to show very much of it. Okay. And we get all kinds of neat graphs from it. You get rose patterns, snails, and cardioids, which are like hearts. Okay. So you see the arm is rotating from 0 to pi over 2 there, and then there's that R value on it, which is kind of going in and out. Okay. So you can see the R value is sliding up and down on the arm, and as it slides, it traces out these curves. See how it's tracing out. Okay. So you can use a table to get it done. Usually what I do is like draw, instead of the table, I just draw the graph of 4 sine theta, like I would back in chapter 4. And if you want to see some animations, you could just go to YouTube, and all I did was type in polar graphs and animation, and I got what I got. But usually I use this computer program, which he's using in the video there. That's usually what I have set up for class. But thanks a lot, Pandemic. Anyways. Section 2 then, this is kind of the method I use. Instead of a table, you just literally graph the thing out. So back here, instead of drawing the table, you could, all right, so pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, and then graph 1, 2, 3, 4, 1, 2, 3, 4. So it goes up and down. It's the same thing as a table, except you can guess more values on the graph. So at like pi over 12, it's barely at 1. So it's probably in here, and then it's going to curl back up and around. So anyways, yeah, call these theta R graphs instead of XY graphs. So you're going to put the theta is kind of like your x-axis, and r is like your y-axis. So again, let's do this problem that we did above, but instead we'll let's alter it just a little bit. The problem with altering it a little bit is you kind of will end up maybe with a different graph at the and a real small altering will end up with a real big change. But anyways, let's look at an example. It's very similar to this one. Instead of using sine, let's use cosine and see what happens, right? So we'll say r equals 4 cosine of theta, and in this case, I'm going to graph that. So you may remember our graphing process. First, we get the amplitude. In this case, it's 4. And then secondly, I usually do the period and the phase shift. Here, the phase shift is 0. There's nothing being added inside of the cosine function to cause a shift. So it's just the period is from 0 to 2 pi. Oops, not the right x or theta inside there. 0 to the theta to 2 pi. And then the tick marks will go by 2 pi over 4, so by pi over 2s. So for the tick marks, you always just take the period, 2 pi minus 0, so 2 pi and divide it by 4. So you get pi over 2s for your tick marks. So the amp, 1, 2, 3, 4, 1, 2, 3, 4, and it's going by pi over 2s on the theta axis. And this will be your r axis. So pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. And then it's a cosine function, so it starts at 1, and then it dips down, and then it goes back to 0, and then it goes back up to, well, it starts at 4, right, because of the amplitude. Okay, and then I just use that information kind of as a table of values, because that's really what it is, just like an infinite table of values, and use those points to do your plotting. Okay, and it's more continuous now, so you could really think of the angles as the tilt of the arm, or the rotation of this arm in the plane. Okay, so let's go ahead and kind of put x and y. I'm going to need 4 circles here to try to space them well. 3, 4. And then instead of putting in my radial arms like I usually do, I'm just going to kind of do one at a time, right? So from 0 to pi over 4, I guess. I'll put that one in. So from 0 to pi over 4, it's going to start where? It's going to start at 4, right here, and then it's going to go to 0 eventually, but before it gets to 0, it's probably going to hit around in here somewhere at 2. Okay, so we'll make it down here at 2, maybe around here. Okay, and then as the curve rotates, or rather as this blue line is rotating from 0 to pi over 4, it causes kind of this curvy picture to develop, okay, like that. Okay, all right. Then from pi over 4 to pi over 2, in this sector, it's going from this red dot here on the r theta graph to this red dot here, and that will be at pi over 2 comma 0, 0. So at pi over 2, angle pi over 2, you get the point 0. Okay? And again, that rotation of that arm kind of causes this curvy effect. Okay? And it should be more symmetric than what I've drawn. The more points you put in, the better it looks. Anyways, let's go again another pi over 4, so to right here. Okay. Once you get to this place here, which is 3 pi over 4, your r value will go negative. So it'll be not on the positive side of the arm, but on the negative side of the arm. So let's sort of, somewhere around -2, maybe in between -2 and -3, will be -1, -2, maybe about right here-ish somewhere. Okay, so it's rotating on the negative side of this arm. And then from 3 pi over 4 to 4 pi over 4, which is, of course, pi, it's going from negative 2 point something down to negative 4 right here. So it'll actually sort of draw out this thing, and it gets right back to where it started. Okay, so actually it looks like we're going to start repeating itself, and you can tell if you go from just pi to 5 pi over 4. In this sector, you're going from negative 4 to negative 2 or something. So it's like negative 4 here, and then on the it's retracing itself in that sector. Okay, so what you're ending up with is this kind of, it should be a perfect circle, and that and this new kind of orientation because of the cosine function as opposed to the sine function up here. Okay, so it's important to note how far it took you to trace these things out. In the first example, we went from 0 to pi to trace the entire thing, and that started repeating. It was the same case down here. It just takes from 0 to pi to trace the thing. Okay. In general, there's two kind of graphs here, and we want to, in this section, kind of classify all the different forms, like you would classify a parabola, and then a cubic, and then I don't know, a straight line, and an exponential graph, a log graph. We want to do the same thing here. And in general, we've kind of looked at just two cases, but we have two circles, basically. In general, we have two different circles and two different orientations. The first one we saw above was the sine version, which always looks like this. R equals A sine theta. And the A, you may think, well, does that turn out to be the radius? That's actually the diameter. Okay, so up here, 4, you could see is the diameter going straight across the circle here. Okay, so A would be diameter. So A over 2 would be the radius. The other orientation that we saw in the second example then, our circle was like this, and that formula R equals A cosine theta, of course, where again A would be the diameter. So 4 cosine theta gave us a radius of 2 on the circle, and that's just a very poorly graphed circle. Okay. Sort of the next kind of set of graphs we have are called cardioids, and they look like little hearts. Cardio, as in cardioid. They're in the book. If you look in the book, they're included in the set of what they call limnosons, that's basically French for, and it's limaçon, the book is saying. That's French for snail, because in some of the forms they kind of look like maybe snails with a head and a shell. But this is also called a cardioid in Calc. I teach it, you redo it in Calc 2, I believe. So anyways, let's look at one of those guys. This is checkpoint 2. And we have R equals 1 plus cosine theta. When you graph this guy, remember, so there's an amplitude. The thing in front of the cosine is just 1. There's no phase shift here. The period is the traditional period, and the theta is just in between 0 and 2 pi. There's the tick marks, of course, it's just 2 pi over 4, so pi over 2. One thing that's maybe a little different that we didn't spend a lot of time on is this guy does have a vertical shift upwards. Okay, so it's vertically shifted by this value here, 1. Okay, so I want to make note of that. There's a vertical shift of up 1. Okay, so let's go ahead and graph this thing in the r theta plane, and then we'll go to the polar coordinate system. So again, theta is on the x-axis and r is on the y. The amplitude is at 1, but it's going to be shifted up 1, so it's kind of like you get a new center. You could, of course, graph it and then shift it. So these are pi over 2. 2 pi over 2, 3 pi over 2, 4 pi over 2. And originally, let's maybe draw it in blue or something. Originally, it's the traditional cosine function. So it looks like this. But then it gets shifted, all these points get shifted up 1, right? So it goes up. Let's put the new guy in red. That goes up to there. This point goes up to there. That goes up to there. It goes up to there. And then finally, that goes up to there. So our graph looks like this. Okay, let's go to the polar graphing now. Looks like we need basically 2 circles. And then kind of rotating out. I guess I can go by pi over 4s again. This is x, this is y. And from 0 to pi over 4. 0 to pi over 4, it's decreasing from 1. So if you look on the graph, I'll put it maybe in yellow. So it's decreasing from 1 to maybe 3 halves. Okay. So on my polar graphing system, it starts out it decreases from 2, right? So it starts out at 2, and then it decreases to like 1.5 at pi over 4. And so as the angle moves, you kind of get that curvy sensation like that. And then it's going from pi over 4 to pi over 2. It's going from that 1.5 down to 1. Okay, so on the graph, so we go to pi over 2 now, rotating in that direction. It's decreasing to 1 here. So it's that curvy sensation to 1. And then on the theta r plane, it's going to like 0.5 at 3 pi over 4. So 3 pi over 4, it's going down to like 0.5-ish here. Okay. It's still that curvy kind of graph. And then it's going to 0 at pi. So as it goes from 3 pi over 4 to 4 pi over 4, it'll go from like 1/2 to 0. And then it kind of hits right here. Okay, and that puts us we're at 2 pi over 2, and then it's going to start increasing again. Okay, so it'll just kind of do the reverse picture, so it'll go out here, and then at 3 pi over 2, it should be right here. And look, there's a bit of symmetry going on, right? So I can kind of cheat a little bit and say, well, it's just going to kind of do what it did before and kind of come back around like that. Okay, so you start asking yourself, well, is there some sort of symmetry I can take advantage of, like I did with even functions, in particular back when you were graphing in pre-calculus. If you knew that a graph was even and you had maybe graphed half of it like this, you could go ahead and graph the other half just from the fact that it was even. And that saves a lot of time, especially in these types of problems, right? And it turns out that that's definitely the case. And I just want to note how far it took for us to graph this. We actually went from 0 to 2 pi to graph the thing this time. Okay. So the other points on the other side of the graph were here, 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 and then here. Okay. Right. So anyways, we want to get this idea of symmetry included. I mean, to be honest, the symmetry ideas are kind of hard to remember in the long run. So The next time you see this, it'll probably be in Calc 2 if you keep on taking math, which is probably like a year from now, right? So you probably would have forgotten the symmetry stuff. My hopes is that you remember kind of the table, or maybe even doing the r theta graph and then going to the polar coordinates. The symmetry stuff, though, is they do take time in the book to go through it, so we also want to go through it. It's a lot like what you did in pre-calc with even and odd. Actually, in pre-calc, they actually looked at origin symmetry as in a x-axis and y-axis. It's a lot like that. So let's take a look, and it does help. I mean, it makes things a lot quicker. But anyways, let's take a look. So graphing with symmetry. So this graph that we just did has, in particular, sort of a polar axis symmetry, right? That positive around the positive x-axis. If you rotated it around the x-axis, it's the same on both sides of it. Okay. The other kinds of symmetry are pole symmetry, which is kind of like origin symmetry, and then y-axis symmetry, which is the line theta equals pi over 2. Okay. So those are the three types. The tests, again, are a lot like what you saw in pre-calculus. So let's take a look at the examples. The first one is polar axis symmetry. So if you have something right here that's given the coordinate r comma theta, this other point down here on the other side of the polar axis, which is the x-axis basically, that point will also be included on the graph, so that'll be at r comma negative theta. Okay, so this is polar axis symmetry, or theta equals 0, the line theta equals 0 symmetry. Then there's the line theta equals pi over 2, or in other words, y-axis symmetry. So y-axis symmetry, and basically if you have the point r theta on your graph, you'll also have the point negative r negative theta. Okay, so if you took the angle theta and then made it negative, you would end up here. So this point would be r comma negative theta. And then if you make the r value negative, you end up on the other side, and there's the negative r negative theta value that we're talking about. The last kind of symmetry then would be the pole symmetry, which is basically just origin symmetry. So pole symmetry. So if you have the point r comma theta on the graph, then you also have the point negative r comma theta. So you just kind of go in the other direction by negative r, but keep the same angle. Okay, to test then, what you do is substitution. So for a polar axis test, you replace theta with negative theta. If you get the same equation right back, it has that type of symmetry. The only difference between this and pre-calc then is in pre-calc, if it didn't work, you knew it didn't have that kind of symmetry. Okay? That won't be the case here. Here, if it doesn't work, you can't really say anything. You really don't have a conclusion. So anyways, let's look at an example and see how it goes. So we have r equals 1 plus 2 cosine theta. Okay. All right, so first, and you can kind of see how the replacement's going to work by looking at the little pictures. And the first kind of replacement is to replace theta with negative theta, okay, to check for polar axis symmetry. So I go r equals 1 plus 2 cosine of negative theta. The cosine of negative theta is just cosine of theta. So this will be r equals 1 plus 2 cosine theta. In other words, it's exactly the same as where you started. In other words, it has polar axis symmetry. Okay, so polar axis symmetry is confirmed. Okay, all right. The next one then we want to try for y-axis symmetry. So we're seeing if what happens when we replace r and theta with negative r and negative theta. Okay. Okay, so negative r equals 1 plus 2 cosine of negative theta. So negative r equals 1 plus 2 cosine theta, and that's clearly not the same thing as what we started with. Okay. So you don't want to say that there's no y-axis symmetry. You're just going to say, I don't know. So you could say no conclusion, inconclusive is probably what the book will say. So I'll just say inconclusive. So I don't know, basically. Okay, and then for polar symmetry, you're just replacing r with negative r and seeing if that leaves the equation unchanged. So no, right? That's not going to work either because you're just going to end up with what we got in the previous test. So for pole axis, again, it's inconclusive. In other words, we're not sure. Okay. We can go ahead and graph this guy and see what we're getting. So first, the amplitude, A value is 2. Secondly, your period, there's no phase shift. Again, the period is the traditional period from 0 to 2 pi. The tick marks, we're going pi over 2s. And then there's a vertical shift up 1. Okay. Let's take a look then in the r theta plane at this graph. So amplitude 1, 2. And so cosine, let's draw it originally in blue. Let's get some tick marks as well. 3, 4. Pi over 2, 2 pi over 2, 3 pi over 2, and then 4 pi over 2. Okay. So let's put it originally in blue here. It's a cosine with amplitude 2, so it should look like this. Didn't mean to put that in black. And then it's going to shift up 1 tick mark. So the new center is kind of like right here. And all the points, I'll put this in red. All the points get shifted up 1. So this gets to here. This point will go to here. This point will go to here. This point will go to here. Finally, this point will go to here. And our new graph will look like this. Kind of. Okay. We want to then graph that in the polar coordinate system. So let's go ahead and do that. I need to go out to 3 circles. 1, 2, and then 3. And I can go like by pi over 4s again if you wish. So here's 1 pi over 4. Rotating like that to pi over 4. Looks like the little red dots will go from 3 to about 2 in the first rotation. So I'm out at 3. And then I dip down to maybe around 2. And then at from pi over 4 to pi over 2, I'm going to go and dip down to 1. So it should end up about right there. Oops, I want to put those dots in red. So I should see something looking like this. And then from pi over 2 to, oops, I'll put those in blue. From pi over 2 to 3 pi over 4, that rotation. Pi over 2 to 3 pi over 4. Looks like it's hitting at 0 around there somewhere. So it hits in here somewhere, maybe. And then from 3 pi over 4 to pi, it's going to -1. Okay, so that'll be a little bit weird. It's kind of going on the negative side and then out to -1, kind of like this. Okay. And then, whoops, so let me check it. Maybe somebody's in my office now. Okay, so yeah, and here somewhere it's going to hit at 0 somewhere. So this is a little difficult, right? There's some weirdness going on, and what's happening is it's kind of going negative at some point, and then it's kind of curling in, and it's going to end up at -1 right here at pi. Okay. Okay. So again, as it goes from pi over 2 to 3 pi over 4. So pi over 2 is at 1, and then 3 pi over 4, somewhere in there it's going to hit 0. Okay, so somewhere in there it's going to curl in and hit 0. And that's what's happening. Maybe I should put that in a different color. Let me put it in yellow. It's not letting me roll all over it. Putting it in yellow. That's this little corner right there. And after it hits 0, it's going to go on the negative side of your sort of angular line. Okay, so it's going to be like over here, and then it's going to curl all the way up to -1 at pi. Okay, and then because it has that symmetry, that polar axis symmetry, it's just going to double over on itself. So it's going to kind of curl back around and then increase back to 1 and then go like this. And that's the snail. Okay, so it kind of looks like a snail with a snail head right here, and then he has a shell. It's supposed to look like that, the snail. My picture's pretty bad, but it's kind of the idea. Okay. Make it look a little prettier. And then it goes in to make it the head, and then it comes back out like that. Okay, so snail, or limnason, which is French for snail. Okay. In general, what do these snails look like? So let's go ahead and kind of just talk about that for 1 second. This class of polar graphs, if Jeffrey gives me the black pen again, that would be nice. So in general, we have the limnasons. I keep calling it like limnasons. I think it's just limnasons. Let me look in the book. It's not like you're going to be at some sort of party talking about it, are you? But yeah, it's limason. They give you the pronunciation in the book. But anyways, the formulas that give you these R equals A plus B sine theta, or R equals A minus B sine theta, or R equals A plus or minus C B cosine theta. Okay. And we have A is always greater than 0 and B is greater than 0. And what do they look like? So when the ratio of A over B is less than 1, like we have in this case, so A was 1, B is 2, so 1/2 is less than 1, you get the kind of the one with the snail head. Okay, so you'll get the snail head version. When the ratio is equal to 1, it's kind of like a mild version. It's actually the cardioid version. Okay, so the snail head kind of gets nullified as you go through these variations. Okay, so in the cardioid version, it should be a little rounder, like it's something like that. Anyways, they'll have polar symmetry to them. So if you get half of it, you're kind of done. Jeez, that's still not very good, but you get the idea, right? And then when the ratio is in between 1 and 2, whoops, 2, you get kind of sort of just an indentation on the thing. And then it's almost circular when A over B is greater than or equal to 2. Okay. Kind of have to do a double take. but it kind of goes flat right there, and then it zips back around. Okay. Okay. Let's see what else we got. So the last, I believe this is the last type. No, we still have rose curves after this one. Second to last type is the limnisates. Okay. So this is, I think it's section 4 in my notes. Limnisates. So these guys have square parts to them. So r squared equals a squared sine 2 theta, or r squared equals a squared cosine of 2 theta, and a is not allowed to be 0. Let's take a look at one of these characters. Example, r squared equals 9 sine of 2 theta. And we're going to go through the symmetry for this guy. So first, again, let's kind of remind ourselves how these work. The polar axis symmetry, if you have r comma theta, you'll also have r comma negative theta. So we're replacing theta with negative theta, so you get r squared equals 9 sine of, it'll become negative 2 theta. Sine is odd, so this will be r squared equals negative 9 sine of 2 theta, which is not the same as the original, so no conclusion on the polar symmetry. Polar axis symmetry, excuse me. So this is polar axis. And then the next type is the theta equals pi over 2, or y-axis symmetry. So if you have r comma theta, you must also have negative r and negative theta on the graph. So theta equals pi over 2. So let's put those in. You get negative r squared equals 9 sine of negative 2 theta. This will be just like the last one, right? So the negative will go away because of the squared part there. But on the other side, it's an odd function, so you have to factor a negative kind of out to the front, and then it's inconclusive. Okay. Then finally, for pole symmetry, just around the pole, if you have r comma theta, you automatically have negative r comma theta. This time that'll be true, right? It will have pole symmetry. So you have negative r squared equals 9 sine of 2 theta. So you have r squared equals 9 sine of 2 theta, which is, of course, the same. So yes on pole symmetry. Okay, so let's go to it and try to kind of graph this. I gotta sneeze. Sorry. Anyways, for this one, I don't really know how to graph, square roots. What I'm going to do is a table instead. I'm going to take r and say it's plus or minus square root of 9 sine of 2 theta and kind of work it that way. I'm going to go by pi over 6s, so theta and r, and then we'll kind of see what happens, right? So 0, pi over 6, and you could just go to your calculator on this guy, right? 2 pi over 6. I'm going to go all the way to 12 pi over 6. 2 pi over 6. If you allow me to, I'm just going to write 4 for 4 pi over 6, 5 for 5 pi over 6, etc. 6, 7, 8, 9, 10, 11, 12. Okay. And then I'm just going to plug it into my calculator. Oh my God, this is 0, 2.79, 2.79 again, 0, this is undefined, 0, 2.79, 2.79, 0, undefined, and then back to 0. Okay, so let's go to our polar coordinate system and graph this junk. Need to go out to about 3. Oh gosh, and I'm gonna graph it in red. So 0, 0. Maybe I should get some angle lines here that just aid in the graphing process. So these are going by pi over 6's. Okay, 0, 0. Put these in red. Pi over 6 is 1, 2.79. And then 2 pi over 6, again, is 2.79. And then 3 pi over 6 is pi over 2 is back to 0. Okay, so it's going to go kind of out, and then back in, and then back to 0, right? And then 4 pi over 6 undefined, 5 pi over 6 undefined, 6 pi over 6 is 0 again, and then 7 pi over 6, it's going to jump out to 2.79, and then 8 pi over 6, 2.79, and then back to 0. So it's going to jump out like this, and back to 0. And you can see there's that pole symmetry straight through the origin. The cosine version, then, if you kind of think about it, the cosine's an even function. It's going to have that pi over 2 symmetry. It's also going to have the polar axis symmetry. And so what do these guys look like? This one always kind of looks like the kind of tilted bow tie. And then this guy looks like a horizontal bow tie due to its symmetry and where it's starting. Okay. Let's move on to Rose curves. So this finally then is the last type that we'll look at. People get kind of crazy like with these. If you're into art and stuff, you could like fill up a sketchbook just with various kind of curves. They look pretty cool, really. But I don't know. I've never gotten that into it. Anyways, R equals a sine of n theta. R equals a cosine of n theta. I think the book probably goes through and tells you, what the n stands for. So if n is even, you'll have 2 times n petals. If n is odd, you have n petals. Okay. And the cosine versus sine is kind of the orientation. It'll be like rotated a little bit due to whether you use sine or cosine. Okay. We want to make this problem the video quiz, by the way. So this is problem 27, video quiz, video quiz, video quiz. It's also going to be the last problem in this section. Video quiz, video quiz, video quiz. Okay, so this will be 4 sine of 3 theta. Video quiz, video quiz, video quiz. Again, I'm going to go through all of the material. So we have an amplitude of 4. Secondly, there's no phase shift, but the period is something we have to worry about, right? So we have to take the 3 theta and wedge it in between 0 and 2 pi. And then divide everything by 3, so you get 0 less than or equal to theta, less than or equal to 2 pi over 3. And then finally get your tick marks. So you just take 2 pi over 3 and divide it by 4. In other words, multiply it by 1/4. So that's going to end up being pi over 6, pi over 6's. So we go to your r theta plane. So this is theta, this is r, and I'm going by pi over 6's. And amplitudes 1, 2, 3, 4. 1, 2, 3, 4. It's a sine function, so it starts at 0. And then it goes like that. 1, 2, 4. And then it's going to repeat itself. So rather than drawing it over and over a bunch of times, what I'm going to do is cheat a little and just say, all right, this will be 5 pi over 6 here. This will be 6 pi over 6, etc. Okay, and then instead of writing 7 pi over 6, if you allow me to, I'm just going to write 7, 8 pi over 6, 9 pi over 6, 10 pi over 6, 11 pi over 6, 12 pi over 6. Okay, so if I want to know what the r value is at 11 pi over 6, I just go right here, and the r value will be -4. Okay. Okay, so now I want to go to my polar coordinate system and start worrying about graphing this thing. Okay. So I'm going to need about 4 circles. I made them way too small. Give me the eraser, please. Sorry about that. Let's make them a little bigger, right? Now they'll be too big. 2, 3, 4. Okay. I'm going to put some angle lines in there, so I'm going to go by pi over 6s. Well, let's just go one at a time, right? So the first pi over 6 is like right here in that little sector. Okay, so I start at 0, and then it's going to get traced out to pi over 6. It'll be 4. Right? So from 0 to 4 is what I just traced out. Then the next sort of angle from pi over 6 to 2 pi over 6, from here to here. That will go from 4, you can see in the r theta, or the theta r graph, goes from 4 back to 0 at, where are we? So this is pi over 6. 2 pi over 6 is pi over 3. So from pi over 6 to pi over 3, it goes back to 0. Okay, so from pi over 6 to pi over 3, it's going to curve back to 0. Okay. And then from 2 pi over 6, which is pi over 3, to 3 pi over 6, which is pi over 2, it's going to go to negative 4. Okay? So that's to that angle. So going from here to here, it's going to start out at 0, which is right here on the arm. Right? So it's going to go 0, and then it's going to go negative to negative 4. And then from 3 pi over 6 to 4 pi over 6, oops, I'll put these in blue, 4 pi over 6 right there. From here to here, we're on the negative side, so we're actually, you're kind of thinking you're over here, really. So it's going to go from negative 4 back to 0. And you can see that on the plot up here. It just takes a little bit of practice. Once you practice it enough, hopefully it'll be kind of intuitive the way it's working. Anyways, from 4 pi over 6 to 5 pi over 6, you're starting to repeat itself. So I'm drawing it in yellow now, going from there to there. So now it's going to, where are we on the polar graph? From 4 pi over 6, which is 4 pi over 6 to 5 pi over 6. It's going from, so where are we? 4 pi over 6 to 5. Seems like I already did 4 pi over 6. So I went from, yeah, I already did 4 pi over 6 to 5 pi over 6. So what the heck is going on? What did I do wrong? Well, I went from 3 pi over 6 to 4 pi over 6, which is 3 pi over 6 to 4. Sorry. That's right here. So what I did was I skipped 1. Okay. So let me kind of edit this a little bit. I feel like I should start over. Sorry. Sorry, guys. Just bear with me here. It's not going to kill us to do it again. So 1, 2, what did I say? I have to go 3, 4, and then I need to regraph this thing up here. So it starts at 0. It was a sign, right? Yeah. It starts at 0. and does that. Okay, so again, from 0 to pi over 6, that's this angle right here, it's going from 0 to 4. So it's going from here to here. And so 0 to 4. Then from pi over 6 to 2 pi over 6, which will be like this angle here, it's going to go from 4 to 0. 4 to 0. Okay. So it's basically going back to 0. And then and this is where I screwed up last time, from 2 pi over 6 to 3 pi over 6, which is really pi over 2, it's going to, from 0 to negative 4. So it's actually going from 0 to negative 4 like that. And then from 3 pi over 6 to 4 pi over 6, which will be from here to here. And we're actually on the other side of the arm. So we're going from here to here. Because we're negative, it's going from negative 4 back to 0. So it's going to go like that. And then from 4 pi over 6 to 5 pi over 6, from here to here, it'll go back positive, right? So it'll start repeating itself. I'll put those in yellow now. It'll go from 0 to 4 in that little sector, 0 to 4. And then from 5 pi over 6 to 6 pi over 6, which is basically going from here to here, it's going back to 0. Right? So it's going from here to 0. So it's going from here to 0. And then from 6 pi over 6 to 7 pi over 6, from here to here, it's going to negative 4. And if you look on the graph, where is that going to go? It's just going to start repeating itself, right? So you'll be over here, basically going in this direction, and you'll start retracing. So we're able to trace out the entire thing on the interval from 0 to pi, because it basically went all the way up to 6 pi over 6. And then we get a 3-petal flower, which is what the book predicts. So if you have an odd n value, so our n value in this case was 3, so we'll have 3 petals. If you're dealing with an even number, like 4, you'll end up with 8 petals. Okay. So really cool stuff, you know, graphing this stuff. And like I said, you may remember in the previous video, this stuff's used in astronomy for orbits of celestial objects. Okay? So, you know, satellites and moons and stuff like that. Back in the day, the formulas they used to predict the motion of the planets in the sky, because if you're on Earth and you're looking in the sky, the planets kind of sometimes have this kind of form to them. So they would use these polar graphs to kind of predict the movement of the planets, but they were never perfect, you know, because they knew kind of that after a while that these planets were orbiting the Earth, but they still didn't have the mathematical formulas, really. They were kind of complexified from the time that we didn't know how the planets were moving around with respect to the sun and Earth. Did I say the planets were moving around the Earth? I didn't mean to say that. That's what it looked like to them, though, right? And they would look in the sky and they see these patterns. And so they got really good, actually, at predicting the movement of planets using these weird kind of patterns, epicycles, I think they're called, and paracycles. And all of the math that you're seeing here kind of comes from there. But later on, then they finally figured that they could predict it better using just orbits and things like that, ellipses and parabolas and hyperbolas, which I think you probably looked at those in pre-calc. Anyways, astronomy is kind of where this would be applied, if you're wondering. Okay, so I'll leave it at that, and thank you for watching, and we'll see you next time.